Suppose you're building an HTTP API or a user-facing web application, and it has 100 different routes that you need to generate URIs for, and each route has 1 or 2 parameters that you need to read from. How do you manage this? Hi, I'm Austin Wright. I'm a web application developer, the editor on the JSON schema specification, and for the past few years I've been researching schema-based grammars. Let's take a look at the syntax of a URI. It contains 2 parts that are specific to a given server, the scheme and the authority. The URI also has a path and query parts that can be assigned meanings by the server as it pleases. HTTP servers must encode and decode these URIs when talking to clients. This is a common task in APIs. You map a database record to a URI, and then you give this URI to a client. Now, when the client requests this URI from you, how do you know what it maps back to? In general, the most basic operations in any networked application is encoding, then decoding data, or marshalling and then unmarshalling data. When you're returning JSON in a response, you might have code that looks something like this, where first you specify how a JSON document will be laid out, and then you serialize it into a string that's transmitted over the network for other parties to receive. You can even use a language like ABNF or JSON schema to define what the data is expected to look like, including how to generate it or parse it. These formats are opaque. They don't have standardized semantics, meaning that the data is defined by the server that it's found on. So on one server, this document might talk about railroads. On another server, the same document might be talking about statues and art museums. URIs work a little bit the same way. So how do we express a URI schema? The earliest strategy for this was just using HTML forms. This form describes to user agents how to search GitHub for snippets of code. You can read the values in a request, probably using the get superglobal like this if you're using PHP. And then you probably got ransacked by a cross-site scripting attack and suddenly remembered that you must HTML encode your output. URI templates are a more generic way of constructing a URI. In addition to describing query string parameters like HTML forms, URI templates can also embed variables in almost any part of the URI, as well as express some simple operations such as substrings. It's used internally in web application code and is suitable for exposing to end users so that they can craft their own URIs from a template. It's described in RFC 6570, and it's designed so that APIs could describe URI hooks to each other, including parameters. Here's a small selection of some URI template features. You can include a directory that has prefixes or suffixes. You can find a substring on a variable, such as selecting just the first character or the first 2 characters. You can build query string parameters, as you see in HTML forms, or you can do hierarchical /delimited components, like here. Notice that the URI template automatically escapes special characters as needed. Now, if URI templates are designed for encoding URIs, what about decoding them? Can we treat URI templates as a schema to unmarshal the URI back into usable data for your application? Let's take a look back at JSON. Once we have an encoded JSON document, someone has to decode it. In ECMAScript, this is easy. The inverse of JSON.stringify is JSON.parse. Now, in JSON schema, or with a document type definition, or with a URI template, they are similar in a very important way. They let you describe a language, a way of describing if a string is a member of some infinite set of strings. JSON schema lets you describe a language of JSON documents. That's a subset of all JSON documents. A DTD lets you describe a set of XML documents, and so on and so forth. But so far we haven't really seen a schema-based URI parser. So to theorize how this might work, let's take a look at how formal grammars work. One of the important things to realize about formal grammars is the principle of least power. The idea that we should use the least powerful class of languages that accomplishes the job. What this means is the more expressive a language is, or the more powerful it is, the more nuanced that you can describe what is included and what is excluded from your language, the fewer useful things you can do with the data found in that language. It makes sense, hopefully. This comes up over and over whenever you're designing an architecture. The more powerful a system is, the fewer different ways you can use it. This chart illustrates some of the trade-offs that you make when you pick a language system. This is specifically the trade-offs in the Chomsky hierarchy, developed by Noam Chomsky when he hypothesized that human language follows an innate universal grammar. That hypothesis was bunk, but the formulation turned out to be very relevant to computing. The recursively enumerable languages are all languages where you test strings by executing a computer program. The problem with this is there's no guarantees on how much CPU will be used or that the program will ever end. You can't even prove if the program will ever end or not. Really, the only useful thing you can do is just execute the program and hope that it eventually returns a useful result. The context-free languages add some restrictions. You can have indefinite nesting of data structures, but the computer can't peek into this stack without forgetting where it is. So, like if you've ever wandered into the kitchen for your keys and then realized you want a snack, and then realized you have to wash the dishes first, and then you forgot what you were doing, context-free languages are sort of the computer equivalent of that. By adding this limitation that you can only peek on the top of the stack, you can add and make sure that there's an upper bound on how much CPU and memory is required to evaluate a given string. When a language is context-free like this, you can also produce all of the instances of that language that's of a given length, the same way that an infinite number of monkeys on an infinite number of typewriters will eventually produce a given work of Shakespeare. The deterministic context-free languages are a subset of the context-free languages that are not ambiguous and don't require look-aheads, meaning that the meaning of each character is not dependent on a future character or a character at the end of the document. JSON documents fall into this category. If you're not inside a string, then an opening curly brace always means that it's starting an object. An opening square bracket always means it's starting an array. It's never ambiguous depending on what's going to come up later. At this layer, gain the ability to concatenate languages together. So it's possible to write a JSON parser that parses just an endless concatenation of JSON documents without any separators whatsoever. It can see, false, 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 and know that that's 3 different documents. The level that we are actually interested in are the regular languages. Here we eliminate recursive data structures, and in trade we gain the ability to find unions and intersections between multiple languages. These are the abilities we're interested in, because in order to talk about a lot of URI routes at the same time, we need to talk about unions and intersections. So this is really the layer that we are interested in. The interesting part about regular languages is you can describe them using regular expressions, hence the name regular expression. It's an expression of the regular languages. What we want to do is implement the subset of URI templates that are describable with regular expressions. What this means is we want to find a regular expression that exactly matches all of the URIs that can be generated by feeding a given URI template any given input. And if we make one assumption that variables are not reused, it turns out all of the functionality of URI templates can be described with a regular expression. We can describe a URI template that has substrings, explodes, or the plus modifier, and we can turn it into a regular expression. Regular expressions have an interesting property that they can be described with a finite state machine. And likewise, all finite state machines can be turned into a regular expression. You can represent finite state machines visually as a directed labeled graph. So here's what the start of a finite state machine looks like. We use a dot to point to the initial state, which is the state before any input has been processed. We number each state. The order of the numbering doesn't matter. It's purely so we can distinguish between different states in the state machine. And then we consume each character in the input one at a time, and we look for a transition that matches that character, and we follow it to the new state. So this finite state machine matches an H, then a T, then a T, and so on and so forth. The end of this state machine, we have a transition that acts on a range of characters and points to itself. This is how it consumes characters in the query variable. So we follow a question mark, then a Q, then an equals sign, and then the input for the variable. In this case, let's say FOO, foo. And then finally a percent encoded sequence, %20, which is the encoding for the space character. And it lands on an accepting state. We represent an accepting state with a double-edged circle. By landing on an accepting state, we know that the input string is part of the language. If we landed on a non-accepting state, just a circle with a single outline, then it would not be in that language. Or if there is no state transition for that character, then we would fall into what's called a dead state. The rectangle here is a special type of accepting state that I call a tag. There's no character of input that can cause a transition to a tag, but as far as the finite state machine is concerned, it's still in transition to an accepting state. This will come in use later when we optimize the finite state machines and start operating on them. There's one more optimization we can do. By treating a percent encoded sequence as a single character, we can reduce the number of transitions in the state machine. Now, what if we have a lot of routes? How do we know which state machine matches it? We can test a URI against every state machine sequentially, and indeed this is how the vast majority of routing libraries do this. CoreRouter, it converts each route to a regular expression, and then tests each one in series using a for loop. React Router, same thing, but using array for each method. Express Router, same thing, but with tail recursion. Workbox routing, same thing, but using for of iteration. Find My Way is the most interesting router that I could find. It organizes routes into a tree and does a depth first search with backtracking. This produces slightly better performance, especially when there's a lot of routes that are dissimilar to each other. Now, recall that URI templates are regular. This means that we can take the union of all of them together. So here's a list of all of the routes listed on the front page of GitHub's API. And this is what it looks like when we convert some of those to a state machine. This is some of the 33 state machines. The three on the right here are all variations on api.github.com/org followed by different file names or variables. Now it seems like a waste of time to have to repeat the transitions on all three of these. What we can do is when we take the union of these, we can optimize all of this away. So the start of this, it merged all of the states that start with HTTPS together. Then you notice it approaches a fork. Down the left side here follows api.github.com/, or if we see github.com/ with no subdomain, then we follow that one lonely branch all the way down the left. You might recognize this as a binary search tree. The one major difference between a state machine and a search tree is that a state machine can process indefinitely long strings, and it can match multiple different strings to the same leaf, or in this case, the same accepting state. There's one interesting area here. It looks like a shell, where there's state transitions crossing each other and then joining back together. Let's take a closer look at that. Suppose we specify a gist ID that begins with starred, except for the last character. In this case, we skip the transition on D that would normally be from 244 to 261, and we instead jump to 135. Which is the route that contains the gist ID variable. This is how we handle partially overlapping states. But what if the route is an exact match? In this case, what if we follow the path for public? We end up on the accepting state 243, and this matches two routes. At first, it matches, it matches gist/public, and the other route it matches is gists with the gist ID variable. But a URI can only identify one thing. So how do we handle this situation? How do we handle ambiguous or overlapping routes? The first technique is we can simply prefer routes that were inserted first or last. In this example, if we prefer routes that were inserted first, the gist ID route will inadvertently shadow the routes that come after it for public and starred gists. This can cause some amount of confusion. And is there any reason that the insertion order should really be relevant? It seems to me that a route should just work regardless of when it was inserted into the routing table. So my better solution is to detect subsets. If you detect when one route is a subset of another, you can assume that the smaller set has priority over matching the larger set. In this case, the public and starred routes are detected to be subsets of the gist ID variable route. You can use this technique to configure 404 not found routes or generic catch-all routes as well. So here, the most specific route matches blog posts that end in .json, and then slightly more generic, it just matches any blog post looking like URL. And then if it doesn't match either of those, it can trigger a generic catch-all route to trigger a 404 response targeted for your domain name. The best option out of all of these is to simply reduce the scope of the route. So what we can do here is restrict a variable to a certain regular expression. The cool thing about using finite state machines is that we can pick any regular expression we want and convert it to a finite state machine and make that part of the routing table with zero runtime performance cost. Here, we restrict gist ID to the set of positive numbers. In this case, or in this example, it can consume the character 4, then the character 2, and then it lands on accepting state 30, which matches the gist ID. If a letter came in here, or some non-numeral digit, or if it started with the number 0, then it wouldn't match this and we would get no match. Let's zoom out, and you can see that this looks much simpler compared to the rat's nest from before. There's far fewer state transitions. Now, even though there's far fewer state transitions, both of these still execute with the same amount of CPU power. The state transition and the finite state machine can be arbitrarily complex and can have as many routes as you want, and it always executes proportional to the size of the input. Once we know that a given URI matches a particular route, we probably want to recover the bindings for the variables that produced that route. So how do we do that? I researched this a little bit. It seems like it should be possible to recover the subgroups by mapping state transitions to variables and then working the finite state machine backwards. It turns out, though, this is really impractical, and the easiest way is to just use a non-deterministic finite state machine, better known as a regular expression match. You can make a generic form of this, which looks something like this. The ability to run URI templates backwards has implications for API specifications especially. For instance, OpenAPI currently limits the ways that a path can be constructed or defined, but it turns out that most of these limits are unnecessary. You can define routes with the full range of expressiveness provided by URI templates. First, as mentioned earlier, there's no support for reusing variables. When we compile the URI template to a regular expression or a finite state machine, it has no way to look back at previous uses of a variable. So in the second example here, we can look up dictionary/a/Zytham, and it's not going to see any issue with that, even though there is no value for the term variable that could possibly produce that URI. What you can do, though, is implement this in post-processing when you have access to your Turing machine back. All you have to do is test that the character in the first instance matches the first character in the second instance of the variable. And if it doesn't, you just return 404 not found. This is the same thing you would do if you looked up the database record and you found that it didn't exist. Also, this isn't a feature that any known router supports anyways, so I'm not losing too much sleep over this. The bigger limitation is that operations on finite state machines are complicated. The complexity of inserting and reading off of a routing table is a trade-off, and this technique strongly, maximally in fact, prefers reading performance over insertion performance. Another limitation is that URI templates are not always isomorphic, meaning that you can have ambiguous templates like this. And in some cases, you can get a URI where it could possibly match multiple bindings. So does foo match ab.cd, or does bar match that .cd.html? Well, in regular expression land, we call the first behavior greedy, and that's the preferred or the default behavior. The earlier matches try and match as many characters as possible. If we don't like this behavior, there's another option. We can just add a restriction that removes this ambiguity. So we can restrict foo so that it does not contain a dot. And in this case, there is only one possible binding where foo is AB and then bar is cd.html. The final limitation is dealing with unordered URI components. While the path component is ordered, the query string component is not necessarily ordered. It can be the case in many servers that any parameter can appear in any order. You can have A appear first or B appear first if you have both of them. This isn't necessarily true. Servers can be picky about the order, but usually they're not. And this is the behavior that I suggest. So option one is you can normalize the parameter order before you send it to the parser. Option two is you can generate a regular expression that's not picky about the order by using alternation instead of concatenation. Option number three is you can just process the query string portion separately. This is the option that most routers go with. The only downside to processing the query string separately is you lose the ability to talk about it as part of your URI schema. For further information, I've written a library that incorporates most of this. You can check out the demo at this link. You can also check out my Twitter feed for web development related things at awwscript, or my website at allwright.name. Thank you very much.